here to give this first 2 hours of introductory talk to my part of the program. So thank you very much, Isabelle, for
Well, thank you very much.
accepting it.
Thank you very much for inviting me and for this great program. And also, I'd like to thank you for that Microsoft fellowship. So thank you, Microsoft, as well, I guess. Okay, so these were 2 hours, right? So of course you don't have to stay for 2 hours if you get fed up after one. And so I gave 2 different titles, but actually it will really depend on what you feel like, right? I mean, if I go slow in the first hour, I'll just go on in the second one talking about whatever I was doing in the first one, okay? I mean, this is very informal. I hope that's okay with you. So, I mean, please stop me whenever you like. And okay. Also, yeah, one small disclaimer here. I haven't been working on geophysical fluids for about over a year or something, so it got me back into that stuff recently. So I hope I have just about everything in my head. But okay, if you ask me questions I can't answer, please forgive me, and I'll just try to find the answers before we meet again. Okay, but it was very nice getting back into that stuff, and I hope to do more of it during this program. So what I'd like to do, at least to start with in this first hour, is to describe some methods in the asymptotic analysis of geophysical fluids. So that's very general and too general. So actually what I want to do is just take a very simple model, the simplest I can think of, and on that model describe different methods you can use, right, to try to derive some asymptotic properties, okay? So maybe I can give you some keywords which I'd like to discuss during those 2 lectures. So it's some asymptotics for one very simple system, maybe 2 actually. And so the keywords I'd like to be using are weak compactness methods. That's what I'll start with. Then I'd like to talk about dispersive estimates, which are also known as Strickhart's estimates. Right, I'll also be talking a little bit about resonant interactions, and possibly a little bit about boundary layers. Okay, that might depend on time. And then what I was planning to talk about in the second hour is semi-classical techniques. Okay, so those are very different methods, but basically what I'll be doing is that, at least for those 4, I'll just take one system of 3D rotating Navier-Stokes equations, and depending basically on the boundary conditions or on the way you want to write down the Coriolis force, you'll be using one or the other of those methods to derive some limiting equations, okay? For this, okay, I'll explain what I mean by, for those who mightn't know, what I mean by semi-classical analysis. And this will be on another model, which is a little bit related to what Ben was talking about this morning, which is the shallow water rotating equations. Okay, so that's 3D Navier-Stokes with rotation. And that's shallow water equations with rotation as well. Okay, in the set actually. Right, so let me start by discussing a little bit the model. Okay, so there's really very, very little physics in my model, right? It's just going to be 3D Navier-Stokes to which I add the Coriolis force, and that's it. Okay, but the idea is that these methods are robust enough to be adaptable later on or some other day to other models, and it has been, right? I mean, I don't want to get everything confused by complicated equations. I want the simplest equation possible, or almost. And on that simple equation, I can show you how those techniques work. Okay, but then obviously they work for many other problems. Okay, so I take the 3D Navier-Stokes equations. I'll be calling U the velocity field. So it has 3 components. P will be the pressure. Okay, and as you know, the Coriolis force just comes from the fact that you're writing down the equations on the rotating frame, which is the Earth, right? So, I mean, there are lots of approximations you're going to make, which I'm not going to do here, but you know that much better than I do, so I don't want to start talking about that too much, right? But, so this is the Earth, which is rotating at some velocity omega. And, well, obviously, depending on where you are on the Earth and how large your latitude zone will be, then you have to take into account the variations of this or not, right? Because if I call theta the latitude, okay, then, okay, I think right now, actually, I'll be placing myself in a Cartesian frame, okay, so I just take everything as totally flat, so x2 now is the latitude, okay, x1 will be the longitude, okay, and what I'm going to say is that the influence of this omega here on the equations is essentially the projection of omega onto the radial vector, which will be here the vertical coordinate, like x1, x2, and now x3 will be the vertical coordinates, and so that projection looks like, up to some sign problems probably, 2 omega sine of the latitude, or minus maybe, and u2, where u2 is the second component of the velocity, and 2 omega sine x2 of u1. Okay, that's the only, and 0. Okay, that's a 3D, three-component vector field, and that's the only influence of the Coriolis force. I'll be including the equations. Okay, so definitely I've dropped a lot of things out. Okay, so I don't want to go too much into this, but what I want to emphasize here is that depending on how big x2 is, you can assume this is a constant or not. Okay, so you have that f-plane approximation where you're saying x2 is just varying a tiny bit around some given point. So this will just be a constant. That's the f-plane. The f-plane approximation, I'll just be looking at 2 omega, let's say minus u2, u1. Okay. Whereas if you want to use the beta plane approximation, you're going to write down an expansion of the sign, right? And depending on where you are here, whether you're at the equator or somewhere else, either you expand the sign x2 around 0 or around some given constant, okay? Which means that you have, if you're not around the equator, if you're somewhere in the mid-latitudes, then you would have something, okay, I mean, just linearize your things, so sign of some constant, let's say 1, plus, I mean, I put all constants equal to 1. Okay, plus beta x2. And if you're near the equator, you would have something like beta is just a constant on your x2. Okay. What I'm saying here is that I'm going to write down the 3D Navier-Stokes equations, and I'll be adding to my usual equations either this constant term, which is the rotation of u, right, by pi over 2 times some number, or some variable coefficient term, which will make analysis much more complicated, although it's explicit, or this one, which is still a bit more complicated in the sense that x2 can vanish. Okay?
It's still times
Sorry?
It's still times the rotating.
Yes, of course, yeah. So if you don't mind, I'll write that like u perp. Okay, that's this vector. Okay. So now let me write down the equations. So use my velocity field. So just the usual Navier-Stokes equations. I'll take viscosity equal to 1 to simplify here. And then I'm going to suppose that the Rossby number is very small, and I call that epsilon. So once you put everything with no dimensions, you get a 1 over epsilon here. And then I have my, okay, in general, some function of x2 times u perpendicular is equal to the gradients of the pressure, and then u is divergence free. Okay, then so what I'm going to do in at least the first lecture is discuss what happens when epsilon is assumed to be very, very small. Okay, can I describe what the solutions of this equation look like? And depending on what b is, so first will be a constant, and it might be varying, and also, of course, depending on boundary conditions. Okay. Right. So maybe what I should do right now is just, okay, so that's my problem. Just call it Navier-Stokes Coriolis. Okay, so the question I want to address is the behavior of the solution, which is u here, which depends on epsilon, right? So I might indicate that once in a while, of the epsilon depending on epsilon as a function of epsilon. Meaning if I do have some limiting equation, just like we saw this morning, usually you are able in some sense to derive some limiting equation. Weak limit, strong limit, we'll be discussing all that. But once you know your limiting equation, one thing you could try to do is to extract from information on the limiting equation information on the original equation. Okay, which is sometimes interesting in the sense that the limiting equation could be much easier to handle. Then you hope that for epsilon small enough, you look enough like the limiting equation to be also well behaved. Okay, so that's the point. And of course, this will depend on B. So it will be either a constant or a function. And it will depend on boundary conditions. And so, okay, my boundary conditions will be not physical at all, because basically I'll be either taking my coordinates x to be in the whole space or periodic, okay, or mixtures, right, depending on x1, x2 could be periodic and x3 in the whole space, or maybe the contrary. Or when I'll be talking a little bit about boundary layers, maybe something like periodic in 2 dimensions, and maybe something horizontal, slate, something like that, in a vertical direction. Okay? And the analysis will depend very much on boundary conditions. I'm not looking at all at the equations in a physical domain, right? I mean, this should be omega, right, with boundary conditions. But most of what I'm going to say here just drops down because you don't have any explicit formulations or semi-explicit formulations. Unfortunately, I mean, probably everything I'll be saying here, or almost everything, is true in this kind of framework. Okay, slightly better. I'll be talking a little bit about, when I talk about dispersion, it will be in the whole space, can be in more general conditions, but the rest is really very linked to those boundary conditions. But I'll be explaining as we go along. Okay. Yeah, of course.
I usually call these the 3D incompressible Euler equations because there's no diffusion.
Yeah, there is.
Oh, where's the diffusion? Oh, there it is. I missed it.
Okay, actually, okay, this is most of what I'm going to say is true without diffusion. Diffusion just helps once in a while to get global solutions, that kind of stuff. But I'll show you as we go along. But all those techniques work very well with maybe not that one, but those would work very well. Those two at least without diffusion. Diffusion just helps once in a while, and I'll show you where. Okay. So let's see. So the first question I want to address really is what does the solution look like? And before I do that, maybe the first question we can answer is, at least if I want to see what happens when epsilon goes to 0, the first thing I should have is some a priori bound on the solution, right? Independent of epsilon. If I hope to have a limit, then the first thing I have to check is that I have a bound. Okay? If I don't have a bounded solution, I can't get it. I have trouble getting a limit. So what about uniform boundedness? Okay, well, obviously, this term here, u perpendicular, whatever b is, this is orthogonal to u, right? So obviously, I can write down an energy estimate in L2, just taking the scalar product of u by u and integrating wherever I can, and this will drop out. Okay? So that means that an L2 energy estimate is the same whether I have rotation or not. Okay, so this is an easy, obvious bound I have, which I'll write down here, which is that for any positive time, this is totally formal, right? I mean, I have to prove that I'm allowed to write down whatever I'm going to write, but okay. As much as you can do that for Navier-Stokes, you can do it for this. It's exactly for the same reasons. You get 1/2 of the L2 norm squared plus, okay, here comes the viscosity, the integral of the gradient. That's formally equal to, that's formal, the initial data, which I'll call U0. Okay? And you're not using anything here. If you're in the bounded domain, you just need to have some Dirichlet boundary conditions, right? But if not, I mean, the rotation has just dropped out because it's skew symmetric. Okay? So that tells you, okay, this is formal. That tells you can run through the proof of the Loret theorem of existence of global solutions for Navier-Stokes, 3D Navier-Stokes, exactly in the same way as Loret did. Okay? The first step you do is write down an energy estimate. This thing goes away. You'll never see it again. Okay? So the Loret theorem for 3D Navier-Stokes is true exactly in the same way for this equation. Okay, so that tells you that if you have initial data, so it's not really a theorem, I mean, it's just nothing new compared to Navier-Stokes. If U0 belongs to L2, whatever the domain, then I know there is a solution, U epsilon, which is bounded, so globally in time, with values in L2. Okay, and I know that the gradient of U is bounded in L2 in time with values in L2. Okay, so that's the first good news. I have a family of global bounded solutions. So once you have that, you can say, that doesn't depend on B, right? You can say, okay, now I have this, I can extract a subsequence, right? And by compact this, I know that I have a weak limit point, which I call U with a bar, so it's a U tilde of this morning, okay, as epsilon goes to 0, in the same space. Okay, so if I call dot H1 the space of functions whose gradient is in L2, then I have this weak convergence here. Okay, so that was, I mean, there was nothing to do for that. Now the question, I guess there are two questions we should ask now. I know U bar exists, okay, but what equation does it satisfy? Okay. Now I know this U bar exists. That's question one. What's the equation? And question two, is the convergence strong? Okay, which of course is very different. If I just have a weak convergence, that means there are all kinds of oscillations maybe, or something going to infinity. Something's happening if I have weak convergence, which is not strong. If it's strong, that's much better. Okay, so I'll try to answer those two questions. And maybe I should start by studying a little bit U bar. Okay, so the first thing you can check very easily, which is also what we saw this morning, is that if you have any kind of equation which looks like this, so maybe with the same notation as this morning actually, so capital U plus some Q symmetric operator L, some penalization here, plus any type of nonlinear function Q. Okay, if I know that the solution, okay, let it depend on epsilon here. If I know that U epsilon converges weakly in some sense, let's say in the energy space to some U bar, then clearly U bar has to be in the kernel of L. Okay, that's what we saw this morning. Well, why is that? We'll simply take this equation, multiply it by epsilon times some test function in space and time. Okay, and integrate everything. What you get, this first term, you have an epsilon in front of it, right? dt, you can hit the chi instead by integrations by parts, so it drops out. This one stays, of course, because you have epsilon just canceling this one. Okay, and this one drops out again because of this epsilon here. Okay, so in the end, taking weak limits, you have to have this constraint here. Okay, and that's totally general. That's what always happens. So that's sort of good news, because now it means that I have just to study what the kernel of L is. Okay, what's L here? So L of U is, okay, so just mustn't be a tiny bit careful here. Okay, L looks like this operator here, right? Except you have to remember your divergence free. So you have to project that operator onto divergence free vector fields. Okay, so L of U by construction is a projector onto divergence free vector fields of this operator here. Okay, where P is the projector onto divergence free vector fields of this operator. Okay, so projecting everyone onto divergence free vector fields. So now let's just see, what does it mean for U to be in the kernel of L? Okay, so I don't like this operator very much, but just saying LU bar is 0 just means that there is some pressure, okay, I can call P bar, such that, okay, B of x2 times minus U2 bar, U1 bar 0 is equal to the gradients of P, right? Okay. So, okay, that's pretty easy to solve, because that means in particular, so I'll do this quickly, but you see here D3P is 0, right? So if D3P is 0, then D3 of U2 and of U1 is 0, because they're equal to something depending only on P, right? And on this, which does not depend on x3. So that means that d3 of U1 is d3 of U2 is 0. Okay, so it's 2D, right? And then since U is divergence free, because that goes through the weak limit, then d3 of U3 is the horizontal divergence of U, right, which is 0 because it's a gradient just turned, right? So you also have d3 U3 0. Okay. And if you look at this and you take the curl of this equation just to get P out of the way, you find something like B gradient U has to be 0. Okay, take the curl of this equation, use the divergence free condition, and this is what you get. Okay, so if B is a constant, actually, is that it? No, it's not that at all. It's U gradient B. Okay. The other part is divergence of U, which drops out when you take the curl of this thing, so you get U gradient B. So if B is a constant, this is nothing. It's no more constraint. If B is not a constant, that's just something else you have to remember on your weak limit. So you can prove that's equivalent, actually. So what you can prove, which I won't do because it's strictly no interest, but actually the kernel of L is exactly the divergence-free vector field, such that, so maybe I'll use some notation from now on. I'll write it up here so it won't disappear. I'll always, yeah, sorry, just 1 second. I'll always write UH as U1, U2. It's a horizontal vector field. Okay, so right. So the kernel of my rotation here is all the U's such that the horizontal divergence is 0. Okay, that means horizontal divergence, D1, U1 plus D2, U2. D3 of U is 0. And when B is not a constant, U gradient B is 0. Okay?
Sorry, the second 0, you use the divergence-free condition with
This one, yes. Yeah.
with the first thing.
Yeah.
Okay. Yes.
Exactly. Yes. Yes, with this. Yeah, that's probably not what I said, but that's what you do. Okay. Right. So that's sort of good news, right? Because you see the weak limit only depends on 2 variables. Okay. So that means that what you hope is that U bar satisfies the 2D Navier-Stokes equations. Okay, why is that a hope? Well, in some sense, because if that's true, and if maybe you had strong convergence here, then that would mean that Navier-Stokes, when the rotation is quick enough, looks very much like 2D Navier-Stokes, right? And we all know 2D Navier-Stokes is well post. Okay, so we could hope to use this information to prove that this system here has a global unique solution for epsilon small enough. Okay, so it could be useful. But the thing is, if you want to prove this, you have to take a limit in the equation, of course. I mean, it's got time, so we know that all linear terms will converge very easily, right? So if I know U epsilon converges to U bar, then dt U epsilon converges to dt U bar in the weak sense, right? So all those linear terms will converge. This is 0 if you take a projection on the kernel of L, right? This is gradient. So the only problem, of course, is taking the limit of the nonlinear term. And you can't take weak limits of nonlinear terms. Well, you can if you want, but you have to be careful. Okay. So that's the problem. So that's the first step. Weak compactness is to try to prove. So the new question is, what is the limit, the weak limit of U epsilon gradient U epsilon? Okay, if I only know that U epsilon converges weakly to U bar, how can I get the weak limit of this nonlinear term? Okay, yeah.
Another question about
Yeah.
this term. You're sort of the coefficient's 1, right? So implicitly you're assuming the Reynolds number. You assume something that epsilon is 1 over epsilon is big compared to the Reynolds
Yes,
number.
definitely, yeah.
But I mean, in geophysical applications, that's well, I mean,
Yeah.
epsilon's huge and 1 over epsilon is big.
Okay, that's right.
Yeah.
Okay,
Okay.
this is it's been a long time since geophysical fluids are actually a little bit lost in this model. I totally agree. The thing is, okay, when I'll be talking about boundary layers, if I do, I will be taking a vertical diffusion, which is very, very small. Same ratio as the Rossby number, which is probably better. And also, what I'm going to say here, okay, at the formal level at least, is true if I don't put any diffusion here at all.
That's fine, yeah.
That's better,
I understand that, but when you bring that in, it's...
Yeah, I agree.
Okay.
I agree. This is, okay, maybe I shouldn't put it at all, but it does help sometimes.
Okay.
Okay. At least here, I'm going to prove, whatever I'm going to prove here will be very formal, so you could forget about viscosity, but when you really want to prove it mathematically, I am using some regularization due to the viscosity. So, it's, yeah. Okay, so let's see what that weak limit is. So actually, I'm just going to do the case when b is a constant. Because it's just much easier, okay? But what I'm going to say here, I'll show you at the very end what happens when b is not a constant, and it's also true, actually. But I won't be able to do it on the blackboard without making any mistakes. So I prefer to do just the case when b is equal to 1, just to show you how the thing goes, and then you can believe me, it works the same when b is not a constant. Okay, so in that case, my kernel is just the guys who don't depend on x3. Okay. So actually, to look for this weak limit, what I want to do is take a weak limit of the equation, but I can first project it onto the kernel, right? Because I know the limit is in the kernel. So actually, what I'm interested in is not exactly this limit, but if I want, and it might help, I would be interested in the projector onto divergence-free vector fields, right? Because that's actually in the equation. And also, because my kernel doesn't depend on x3, I can very well integrate over x3. Okay, one comment here, actually. You see, my weak limit doesn't depend on x3. So if x3 is in the whole space, my weak limit is 0. It's not very interesting, right? Because I'm in L2, right? U bar is in L2. That's somewhere here, right? And it also does not depend on x3. So not very many functions which are independent of one variable and still are in L2. Okay? So that means, actually, if you don't want to get something trivial, you should probably assume here that x3 is a periodic box, for instance. Okay? Just not to get something trivial in the limit. Okay, so I'm just taking the average here on the box, and I want this weak limit. So what I can do is cut my u epsilon into two parts, one which is what I would call its mean, its vertical mean, and the remainder. Okay, so where u bar epsilon is precisely what I'm actually interested in, which is the average of u epsilon on the box, on the vertical box. Okay. Now this thing here, you see, if you take the average of this equation over x3, this thing will drop out. B is a constant, even if it isn't, right? Because I know that's in the kernel of the rotation, right? So that means that if I take the average of this equation, there's no more high order term here. That means that dt of u bar epsilon is bounded. There's no more 1 over epsilon in the equation. So u bar epsilon is in fact compact. Can you see here? Yeah, it's okay. So if this is compact, it converges strongly, actually, to u bar. And this guy here converges weakly to 0. Okay, so here I'm slipping a little bit on the proofs here, but we saw that this morning also. It's Ascoli's theorem. I get compactness in space and time. In space, because I have a little bit of a smoothing effect by the Laplacian, and in time, because there's no 1 over epsilon in the equation satisfied by this guy. Okay, so I'm compact, so I can take, again, weak limits, but I also have strong convergence. Sorry, subsequences, but I have strong convergence. Okay, and then this guy just goes weakly to 0. So now, yeah.
Convergence is in space or space-time?
This is space-time. This is space-time. Yeah, definitely, because also, actually in space there's no real problem, right? When b is a constant. Okay, so now to get the limit of the nonlinear term, I can just cut it into two pieces. I say it's the bar times the bar plus the tilde times the bar plus the other guy plus tilde tilde. Okay, so the blue-red terms of this morning. So bar times bar is fine. Bar converges strongly, so you can take strong limits in nonlinear terms, so that converges to exactly what you want. The usual nonlinear term for Navier-Stokes, because you're compact. The cross terms here, they're fine also, because the bar converges strongly, the tilde converges weakly, and weak times strong works. It converges weakly, right? So those two guys converge weakly to 0. Okay? So my only worry is what happens when you have a tilde hitting a tilde, which means weakly converging sequence to 0, hitting another one which also converges to 0, but only weakly. So am I able to take a limit in that term? That's where weak compactness arrives. So actually, for those of you who were at the talk this morning of Bin Chen, you had exactly the same thing happening, and in his case, there was a miracle that was that the integral over f3 of this guy here was exactly 0, which happens sometimes. It happens when you do the incompressible limit of compressible fluids, right? You can do exactly the same thing when you're looking at compressible Navier-Stokes. You want it to converge to incompressible Navier-Stokes. You get this type of stuff, and actually when you project it into divergence-free vector fields, you get 0. Exactly, so that's good. Here, I'm not sure it makes 0, but almost. So what you do, I want to prove that this guy converges weakly. There's no reason, right, a priori. The microphone doesn't work, right?
Your microphone fell out.
That's right. Okay, is that better? Yeah. Okay, so there's no reason for this to go to 0, except if you use the equation. I guess remember where you come from. So this is going to be formal, because to make it rigorous takes a lot of time. It's not so interesting here, I guess. But formally, I want to prove this in the following way. Okay, so let me write this if I can. So, okay, one good thing to do usually, well, often, when this is going to be a small miracle again. So the first time you try to prove that, you just can't because you don't know why it works. You work around with the equations, and then one day you find a formulation which makes it work. Okay, so now I'm giving you the formulation, but of course, you could wonder why you're using this formulation, not another one, but because it works. Okay, so let me write that in a vorticity formulation. So I often get my signs wrong. I think that's it. Up to some gradients, you can write this nonlinear term as this one because you're divergence free, plus some gradient, which is probably not the right one, but something like that. Up to some signs. Okay. Okay, the gradients I don't care about because I'm going to project everything onto divergence free vector fields, right? So this guy, once I project it, will just go away. Now I want to look at this. Now the idea is to write the curl in two ways. Well, in one way, but just write it down. So the d1u2 minus d2u1 term, I'm going to call it omega h, because it's like a horizontal curl, right? d1u2 minus d2u1. And the other ones I'll call capital omega. And I'm going to do something a little bit strange, but that's why it works. I remember this u tilde comes from removing a vertical average from u, right? That means that it's mean free in X3, since I removed it. Right? So I can call it like that if I want. It's just a trick, right? I mean, if I'm mean free, I'm also a derivative of something. Right? So I'm just writing the curve like this because that's what works. Okay, now I go back to my equation, which is up there. So the formal thing, one of the formal things is that I'm going to forget about nonlinear terms. I'm just going to write down the equation on this horizontal curl, multiply everything by epsilon, put to 0 every term which is not of order 1. And then what happens if I take the curl of the rotation minus u2, u1, I probably get something like plus divergence of UH. And that's basically equal to 0. Of course, it's not. It's equal to epsilon times something. Okay, let's just forget about all small terms. Okay, then if I write the equation on this guy here, H, the first two components, okay, what I get, so here I guess you should believe me because you have to do it to be sure, but because I put a D3 here, I get U epsilon H. Okay, when you do the curl, you get actually the horizontal divergence, but that's a D3, U3. Okay, I better check. Because if my signs are wrong, of course, it won't work and it won't be very impressive, right? So, okay, so I think that's it. So, okay, 0 here is wrong also, but it's epsilon times something. Okay, so now I go back to this term and write down what it is. So up to some gradients, let's just write this like this. You have the horizontal part. Okay, so this again, you have to believe me. And maybe I'll just check what it is exactly. Okay, that's it. Because you just do the algebra. This is actually no interest, but it's just algebra, right? And then you have another term, which is plus u3 d3 omega epsilon h perpendicular.
Can I ask a question? Maybe
Yeah.
just notation, but your zeros, you say it's epsilon times something, but the first term on the left-hand side has epsilon times something too, right?
Yeah, but that's order 1, because those guys are going weakly to 0, which means they're oscillating very much. I have no bound. Okay, it is.
So those things are order epsilon minus 1, something like that.
This guy is epsilon minus 1 because it's dt is equal to 1 over epsilon times something.
Okay.
So epsilon dt is only order 1,
Okay.
right? But those guys here only have space derivatives. I'm taking b equal to 1. Okay, so I have no compactness problems in space.
Okay.
Okay. So dt is like 1 over
It's
epsilon.
like it's inertial oscillations, basically. So yeah, okay.
Whereas gradients, thanks to Loret here, I have at least 1 derivative in L2. So gradients are okay. Okay. So of course, I mean, I should put epsilons here, but it would be very, very messy. Okay, so this, once you've computed everything, this is what you find. Now remember, what I want is the average in x3, right? That's what I'm interested in. This guy, if I want, I can pull out the d3 here. Okay, since I want an average in x3, this goes away, right? Minus, the term I forgot is minus d3u3, but the horizontal divergence is equal to minus d3u3. So I get plus divergence I'm almost done. Now I just look at what's written up here, and I hope I haven't made too many mistakes. What's u epsilon h perpendicular? That's exactly epsilon dt of capital omega times small omega. Yeah, I drop all the epsilons. Okay, I've just replaced this by this equation, and then I have a perpendicular here. Okay. Here, divergence UH is minus. Okay, my signs are wrong. This is bad. Okay, this is probably a minus. No, it's not. This is not good. Okay, what? This is a minus. No, this is minus. Okay. Anyway, okay, so let's do this. And then the other one, divergence H is minus epsilon dt. Divergence H is minus epsilon dt of omega times omega perpendicular. Right? I'm just replacing all constant terms by the wave equation I've written here. And the miracle is that this is an exact derivative. Okay, and because it's an exact derivative, with an epsilon in front of it, it goes to 0. Because I'm looking for weak limits, I'm going to take a product by a test function, and the dt will go on the test function, and I have an epsilon in front of it, and it goes to 0. This is weak compactness. Weak compactness is saying I have the product of two things going weakly to 0. I have no idea what the limit is. I use the equation. I use the waves here to use the structure of my equation, the linear part of the equation, okay, to prove that actually this has structure. Right? And if you take the projection onto divergence-free vector fields, you kill all gradients. If you take the projection onto if you integrate over x3, you kill all d3s, and in the end, you get something which goes to 0. Sorry?
Poincare wave.
Yeah.
That
Exactly. I mean, this was known for a long
a
time.
very long time.
For a very, very long time by other methods, which people have done much before, using those things in particular. The only interest of this computation is that now you can use it also with a variable b. I only did it for b equal to 1 because that's the only way I can do it on a blackboard. But now if you do exactly the same thing, but you put b's everywhere, function b, what you get here is this plus blah, 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 lots of terms, which are parallel to gradients b. And now if you remember that the kernel of L, which is here, is all guys which are orthogonal to gradient b, these terms here drop out as well. So what I'm saying here is that this computation has no interest in the sense that we knew for a long time that the guy went to 0 for other reasons, for spectral reasons, whatever. But now the day you want to do the same thing with a variable b, you can't use any spectral argument. Well, I can't at least. So you try to revisit this proof by another method which uses much less explicit computations. Just use waves. Right? So I'm trying to point out. Okay, and this actually was used for the first time. I'm sorry, I'm not giving any references here because there are so many people working on those subjects. So if you're interested in anything I'm saying, you can just ask me who did that, and I can tell you what I know. But at least this thing for the incompressible limit, which is the first time I saw such a thing, was done by Pierre Williams and Mesmoudi in the 90s. And that's the way they could do the incompressible limit in a bounded domain, for instance. Right, using this kind of weak compactness argument, which is much less explicit than using Fourier or whatever. So again, when B is a constant, you can prove this by Fourier transform arguments, that kind of stuff, which is very useful. But everything, all that breaks down when you're in a bounded domain, when you have variable coefficients, that kind of thing. So I think that's useful because it sort of gets you out of Fourier.
The risk of being annoying, I didn't understand how you got those two, next to the curl, how you got those two, the ones you're pointing at, those two equations for the vorticity there.
Right.
Yeah.
I just took the linear equation, removed U gradient Q, and just compute what's the equation on the horizontal vorticity. You see you're taking the vorticity of a rotated U, so you get divergence.
Oh, that's coming from the...
From the equation. Yeah, exactly. That's
Oh,
the
and
point.
you're throwing everything else to the other
I'm
side.
throwing everything else to the other side. No Laplacian, no nothing. Everything is small, so 0. And I'm just keeping the order 1 terms, which is what you could call the wave equation associated to your problem. And I'm using this to say the nonlinear terms go away.
And all those other terms that you threw to the left-hand side are going to die due to weak compactness?
Yeah, they're even strongly, I mean, there's an epsilon in front of them. So.
I'm sorry, remedial question again. You had the epsilon d by dt, you said it was order 1 a minute ago, but then now you have it 0.
Okay, that's good.
So,
Right, this is order 1.
yeah, okay, but then there it's...
Okay, but what's true is that if you take this and you multiply it by text function and you integrate, this goes to 0, right? Okay, that's true.
Okay,
But the thing is, this is not the thing I'm looking at. I'm looking at this product here,
right,
right? So, I mean, this is order 1. It goes weakly to 0.
right.
This product is the product of the two guys going weakly to 0. I don't know what happens. So I work on it, I do some algebra, and I find epsilon dt of something. And this goes weakly to 0. It's order 1, but it goes weakly to
But
0.
it goes weakly to 0.
Weakly,
Okay.
weakly. Yeah, I'm not saying more than that. But it's nonlinear, right? That's why I'm happy, because my first nonlinear term is epsilon dt of a nonlinear term.
Oh.
But since I have epsilon dt, I'm happy. But it only goes weakly to 0, of course, and not strongly. Okay. So again, you can do exactly the same thing for variable coefficients, but I won't do that. What I want to look at now is the strong limit. Okay, so maybe we can just remember what we've just proved. So what we've basically proved is that U epsilon goes weakly to some U bar, and U bar satisfies. Okay, so I haven't. Okay, for in the case B equal to 1, 2D Navier-Stokes. Okay, when B is variable coefficients, actually I won't do it right now, but when B, okay, is bounded from below at least, then okay, I can talk to you about it later on if you want. But what happens is that it's so constrained to be orthogonal to gradient B all the time, that in the end the nonlinear term totally drops out, meaning that even U bar gradient U bar. I mean, if U bar is orthogonal to B, you can prove quite easily that U bar is always also orthogonal to gradient U bar. So that's 0. When B is variable and not constant. So this satisfies the heat equation in 2D. Which is sort of strange, right? But if you take the rotating 3D Navier-Stokes equations with variable coefficients rotation, but bounded from below, okay, never vanishing, then in the weak limit, all nonlinear interactions just disappear and you get the heat equation. If it's Euler, you get a constant. Again, that's because the kernel of this operator is very, very small. Okay, so this is proved. This we haven't together, but almost. Okay, now next question, is the convergence strong? So I'll start by looking at the whole space case. Okay, or rather, because of what I was saying, that you can't be in L2 and not depend on the third variable unless you're 0, maybe we could do instead R2 times the periodic case, maybe, just so you don't want something to be identically 0. What's important here for me, very important, is that you should be unbounded in R2, in two horizontal variables. So let's see how this works. So the thing is, the first thing I want to do is forget about nonlinear interactions again, and just look at the linear equation. So where U perpendicular, B is equal to 1. And what else? Viscosity. Okay, so I'm in the whole space. And I only know how to prove this in the case when B is equal to 1, because the first thing I'm going to do now is take a Fourier transform of this equation. Right now, B is variable coefficients, and it won't be so easy to take Fourier. Okay, but now if you do take Fourier, and if you believe me, just write down the matrix this is, right? And you find the eigenvalues of the matrix. You find 3 eigenvalues. In Fourier space, which are 0 and plus or minus I psi 3 over log psi. Okay, so let's see, is that reasonable? Well, I is reasonable because you're skew symmetric. Okay, psi 3 is reasonable because we know that people who don't depend on x3 are in the kernel. So in psi 3 is 0, you're in the kernel. And this is, I mean, I'm not proving anything, right? And this is an order 0 operator, so it looks okay. So you can just compute it, and this is what you get. And actually, the eigenvectors, which are divergence-free, correspond to those eigenvalues. Okay, so the solution is going to be written out with those eigenvalues. So let's do that. So I won't write down precisely the eigenvectors because they're not really useful. But I can write down the solution of T in sine Fourier space as, okay, diffusion, which won't be useful here at all, almost not useful, plus or minus the rotation applied to the projection of the initial data here onto the 2 eigen spaces, right, plus and minus, which I haven't given you here, but there's an eigenvector for plus, one for minus, and those are the projections. Okay. Question, if I have this vector field here, what's the behavior when epsilon goes to 0? Okay. So if we don't know, we can think of easier problems maybe, try to convince oneself that this thing will go to 0 as epsilon goes to 0. Why? Well, an example. So this is what I call dispersive estimates. So what's a dispersive estimate? If you have a linear equation for the moment, okay, with a skew symmetric operator here, a dispersive operator, then forget about the epsilon here. Usually, for some reason I'll try to explain, the solution decays with t. When t goes to infinity, the solution here should decay when t goes to infinity. Let's see an example. The easiest example is Schrödinger. Okay, the Schrödinger equation, dt phi, okay, I don't know what signs you want to put here. Plus Laplacian phi is equal to 0, for instance. Okay, the solution, obviously, in Fourier space is just this. Okay, so I can write it also in the spatial variables up to constants. Oh, I think that's the constant. Okay, up to signs here. I is probably downstairs. X squared over 2t, sorry. Okay, and then phi 0. Convolve with phi 0. Okay. Clearly, if you look at the L infinity norm of phi here, it's smaller than 1 over t to the power d over 2, phi 0 now 1. Okay, it's just obvious, because here's the decay. So this is a dispersive estimate that tells you that, okay, this equation conserves the L2 norm, but the L infinity norm is going to decay when t goes to infinity. Okay, as soon as the data is in L1. Maybe not the case, but if it is, then you have this decay. And the proof is just looking at the kernel, and you see the kernel in L infinity is bounded by 1 over 3 to d over 2, when d is the dimension, right? D was the dimension here. Now that's a bit too easy. Maybe we should look at the example 2 would be the wave equation. dt squared minus Laplacian of u is equal to 0, some initial data. And you know the solution will be something like plus or minus it mod psi. Okay, and it also depends on dtu 0. Okay, something like that. Let's say that dtu at time 0 is 0, to simplify, and then this is what you get. Right, well here it's not so obvious to take the inverse Fourier like I did for the Schrödinger equation. But still, if you work a little bit, you can prove that the solution in L infinity is going to decay as long as the dimension is larger than 1, strictly, by td minus 1 over 2. That's another dispersive estimate. And to prove that, you take again the inverse Fourier transform and use a stationary phase theorem. Okay? You lose one space dimension. Of course, in dimension 1, the wave equation does not disperse. Okay? Now, what happens, just one comment here, if I had epsilon here, which is in my case, of course, you gain epsilon here, right? So that tells you that when epsilon goes to 0, the solution goes to 0, strongly. So now my example here, for the rotation, what I have is plus or minus it psi 3 over mod psi. So the question is, can I apply the techniques people use for the wave equation, for instance, to prove that the solution associated with this also disperses, right? You also have the time decay. Okay, so okay, so I won't do it, but if you're interested, I can show you how to do it. It takes a bit of time, but what you can prove is what? Well, basically, what you have to do to prove dispersion, you just have to be a little bit careful. You won't want psi 3 to come too close to 0, because this would not oscillate at all. Dispersion is just due to oscillations, right? So if this is too close to 0, it won't oscillate. If psi is too large, it won't oscillate either. So if I want to make this rigorous, I should ask for psi 3 not to be too small, for psi not to be too large. Actually, it's the same here. That's true only for initial data which are compactly supported in frequency space. What you can prove in that case is that the solution, which I call the epsilon, at L infinity, time, decays like, okay, up to some constant depending on those parameters here, exactly like the wave equation in 2 space dimensions. So you get 1 over 2. Okay. So this you can prove by using a stationary phase argument, just like for the wave equation. So once you've done that, you're pretty happy, because maybe you know that once you have dispersion, you can get Strickharts. Strickharts means that if you take your solution in LP in time with values in LQ and X for some P's and Q's, this will be smaller than some constant. Okay, so you go from a pointwise dispersive estimate here to a global integral dispersive estimate. Well, not dispersive, but decay. Okay, so this is known as a TT star argument, which you might have heard of.
What?
Yeah.
Oh.
Sorry. Okay. And so once I have this, I think I'll stop here for now, I guess, or maybe just 5 minutes, or 2 minutes, 1 minute, just to say once you have that, you're happy because you're saying the linear equation goes to 0 strongly, right? So now let's look at a nonlinear equation. Well, what you do is you put the nonlinear term on the left-hand side, and you use this type of an estimate again. Okay, I will prove it now. So what I'm saying here is that the 3D Navier-Stokes equations with Coriolis force converges strongly, the solution converges strongly to 0, as epsilon goes to 0. Okay, so maybe just before I finish, we could say this is not very interesting because I sort of told you, since I know the limit is supposed to be 2D, I should be using the 2D equation to prove results on my 3D equation, which I'm not doing because I'm just saying it converges to 0. Well, if it does converge to 0, then after some time, for epsilon small enough, it's very small, right? And you know that for small initial data, we have a global solution for 3D Navier-Stokes. Okay, so this tells you that for epsilon small enough, the equation has appeared. 3D Navier-Stokes with rotation has a global solution. Okay, whatever the size of the initial data. Okay, so I guess I'll stop here. So if you're very tired, please feel free to go and do something more interesting. And what I'll do afterwards for people who are surviving is talk about a little bit about the periodic case, right, where you have resonances. And then maybe I'll skip this and talk more about semi-classical analysis. Maybe it's more interesting for you. I don't know. Well, you can tell me. Okay, thanks for your patience.
So shall we say maybe 10